So near the end of the 19th century, earliest 20th century, they discovered something called a proton, and what they were looking around was for the electron. And in fact, this was considered really fundamental to science, and there was actually a top scientist that at the time who says, look, don't worry about teaching your children, we'll have it all wrapped up in 5 years. Once we discover the electron, it's all done. Then they discovered the neutron. Meant we had to rewrite all of science again. But anyway, there was a scientist called J.J. Thomson. I can never remember whether it's a P or without Thomson. And he discovered if you had a whole lot of stuff together and heated them up, or you heated it up, basically you got these very small particles with the electric charge coming out. And these weighed maybe nearly 1800ths of the mass of a proton, but it had the same charge, but it was negative. Now what he did was he postulated, and he knew this came from the atom. He knew that if you spat these things out, then you ended up with positive charge, so therefore this must have come from the atom. So he came up with the plum pudding theory. It's quite funny because I've got one of my mum's textbooks, science textbooks at school. It still mentions the plum pudding theory of the atom, even though obviously it had probably been disproven quite solidly by that point. So the idea of the plum pudding theory is you have a ball, and in it you've got positives, which are the protons, and you've got an equal number of electrons, because the idea was, well, protons and electrons like each other and you get opposite charges attract, so they form together and make this little clump. They didn't know for quantum physics reasons that that's not going to happen. They didn't know about that at that point. So the hypothesis was that atoms were these clumps of little clumps of protons and electrons. Nobody knew about neutrons at this point. So basically the pudding was the protons, and the little plums or bits of goodies were the electrons. But so this is the J.J. Thomson model. J.J. Thomson had a student from New Zealand by the name of Ernest Rutherford. And J.J. Thomson was charged at the Cavendish laboratory, and Ernest Rutherford became a student of J.J. Thomson's, and then took over the Cavendish laboratory over in England. And using Geiger and Marsden, capital scientists, students of his, and this Geiger is the same guy that invented the Geiger counter, just out of interest, they did experiments, and it led Rutherford to conclude that all the positive charge was in the centre and all of the negative charge was on the outside, and that 99.999% of the space of an atom was actually empty. So Rutherford called this the nucleus, and he ended up with this electron cloud, and he postulated that these went round like planets around the sun. We know that's not true now, but yeah, pretty good for the time. So, and we'll come back to him a bit later, one of his students was a guy called Niels Bohr. He was a postdoc student there for a year or two, who then figured out explained shell theory, and also his great quantum physicist who came up with the Copenhagen interpretation. But let's go back to what we were talking about before with the vicious spectrum. So let's just quickly talk about 8.5 black body radiation. Black body radiation, because this is one of the important concepts that came along, which also helped explain quantum theory, which later. So all objects radiate electromagnetic radiation. So all objects emit EM waves. And I don't know if, turns out not many people have done this now, but when I was a kid we'd have a fireplace and we'd have an open fireplace. We'd have a fire in there and I'd stick a poker, which is a bit of metal which you use to poke the ashes in the fireplace and the grill. But one of my favourite tricks of course was to leave the poker in there, and basically the end of the metal would get so hot that it glowed red. It became red hot. With a common fire I could never get any hotter than red hot, no matter how hard I tried. I mean, I get maybe yellowish a bit, but... And in this case, this is actually emitting visible light. Most of the time though, it's going to emit infrared light. So light with lower energy than visible light. And that's how infrared cameras work. If you ever see an infrared camera, you see the cold stuff's usually in blue and the hot stuff is usually in red. So, and that's because the different temperature gives off different frequencies of radiation. So all pretty much everything gives off EM radiation. Okay, but one of the problems that they had was that they noticed that the hotter you have things, basically back in the day they had a model that predicted how much radiation you emitted. So basically it said as you got hotter, so amount and temperature, as things got hotter they gave off more, the frequency got hotter, and the frequency is related to energy. So if you look at the energy, let's make that frequency. So as the temperature goes up, the frequency gets higher. But if we look at the energy, I'm going to do energy in red, basically the energy went like this. And at some point, basically it said, hey, if the temperature got really hot, it gave off an infinite amount of energy. And that was obviously silly. So what happened was a guy called Planck, and you're going to Planck, in 1902 basically said that back in this era everybody thought this was like the energy the light emitted was like waves coming out on a seashore. So the current theory at that time was waves, was continuous. But what Planck did was Planck said instead of coming out as a continuous wave, light came out in little packets. Or energy, these wavelengths were emitted in packets, and these are called quanta. Or if you're dealing with light, they're called photons for light. But they're still, electromagnetic radiation is emitted in quanta. It's not a continuous wave. It's a bit like if you see a hose. If you watch a hose squirting water, unless you do collimate the water, instead of being a continuous stream, most of the time what you're seeing is lots and lots and lots and lots of drops travelling along. And it appears to be smooth, and that's what happened here with light. These light actually gets emitted as these little packets of energy. And basically what it said was as the frequency got higher and the energy got higher, basically it just emitted less packets of light. So the amount of energy, but that explained a lot of it. So basically it could only emit, at certain frequency as in little packets, and this became the foundation of quantum theory, along with Heisenberg's uncertainty principle. So this and Heisenberg's uncertainty principle basically is the foundation of quantum mechanics. So how much energy is in a photon? So the energy in a photon, and often we'll use the energy will be done, you can do it in joules or you can do it in electron volts, is going to equal H, which is Planck's constant. And again, that's either going to be in joules per second or electron volt seconds. And F is going to be the frequency of the wave. So frequency, and that's going to be given in hertz. So what is Planck's constant? So Planck's constant is H is equal to 6.63 times 10 to the negative 34 joule seconds. Or if we wanted, you should also know this in or basically it's going to be, you might want to check this figure, if we multiply this, H is equal, so if we multiply that by the number of electrons in a Coulomb, 6.63, actually, 3x negative 34 times 6.242 x 18. It's approximately equal, you should check this up and put this on your card, a piece of cardboard, times 10 to the negative 15 electron volts. So as you can see, that's actually a very, very small number, but we're dealing with individual photons.